Basically put on here. Yes. I still use it. Literally, you sit there, stop. I'll be honest, I just like going in with it. Something goes, okay. Like sometimes it's nice out this.
All right, let's get started. We are covering rational functions today. So all things rational is what our lecture will be about. We covered polynomials at the end of last week, right? Today is Monday. And so what we're going to talk about are rational functions and their graphs. Back on tomorrow, we'll talk about inequalities. And we'll finish all of that kind of stuff up. There'll be a quiz that I give you tomorrow afternoon or tomorrow after class, all right? It's a take-home quiz, as a matter of fact. And that would be due when you come back to class on Wednesday, all right? Okay, so when we are talking about rational function, right? A rational function is another category of functions that are somewhat sort of related, I guess you could say, to polynomials, as it's really just the ratio of a bunch of the polynomial functions. So these are three examples of rational functions. Notice that you have a variable in the denominator, right? Our variables in the denominator, and that's what is kind of indicative of our rational functions. Now, here I have just a screenshot of a typical rational function, right? These are the ones that you recognize seeing, I hope, on calculators. Most of the newer operating systems on our calculators will show a function that looks like this. If you have the older graphing calculators, sometimes it'll show a vertical line, and that's just, I don't know, it has to do with the coding of it, and you know, it just can't pick its pencil up and start at the top. So you'll end up seeing a line here, but that's only on the older models. Okay, most of them look something like this. Now, why do you think that is? What do you think is this imaginary vertical line that we have? An asymptote. And what does an asymptote tell us?
Basically, the graph can't go any further.
The graph can never touch that asymptote, right? It can approach it, but it can't touch it, okay? And the reason for that is probably because if I have a variable in the denominator here, all right, what is the one cardinal rule of something that we cannot have in the denominator?
A square root.
Nope. What number can I not have in the denominator? Zero, right? So anytime I have a value that causes the denominator to be zero, okay, then I have an issue, right? I have an asymptote out there because we can't have that value, all right? Other undefined areas are if I have a negative under a square root symbol, right? Or a negative under an even root symbol. We can't have that either. So that's what we're going to talk about then. When we think about our rational functions, we first want to talk about the domain of these functions. The domain of the function, right? So in other words, I'm going to be considering where is, in this particular case, where is the denominator 0? Because that's the value that's going to be not allowed in our domain. So in the first problem here on question A, it says r of x is equal to x over x cubed minus 8. And I'm interested in, again, where the denominator is equal to 0. So I would just simply take that denominator, x cubed minus 8 equals to 0. since it's set equal to 0 and I only have 2 terms, I can simply move the 8 over to the right and I end up with x cubed is equal to 8. And I can take the cubed root of both sides because the cubed root of a cube undoes it, doesn't it? All right, so I end up with x is equal to 2. The cubed root of 8 is 2, right? So the domain of this function says that that number 2 is the one number out of everything that I'm not allowed to have down there, right?
So that's our asymptote?
It becomes our asymptote, but all we're talking about, and I want you to be very clear on this, or I want to be very clear on this, what I'm asking you right now is what the domain of the function is.
So x is less than 2.
No, that's the one number that's not allowed in the domain, right? So there's 2 ways for us to consider this, right? So the 2 is not allowed in the domain, right? It causes the denominator to be 0. And so you can say x such that vertical bar like that is such that, x such that x cannot be equal to 2. That's the domain, right? I can have every number out there but 2. So in set notation, this with the squiggle bars here is considered set notation, right? Set brackets. So in set notation, this says x such that x cannot be 2. I'm talking about the variable x such that x cannot be equal to 2 is how you read that. In interval notation, we have a different way to talk about it. In interval notation, it would look like negative infinity to 2 parentheses union to infinity. So in interval notation, you typically have parentheses on either ends, parentheses or brackets like we're used to seeing. So this is just another way for us to represent the domain. Okay, there's 2 ways for us to talk about domains and ranges, either in set notation or in interval notation. You may see either one. I don't care which one you use. I'll default to set notation if I have a bunch of breaks in it, or I'll use interval notation if I usually default to interval notation. But anyway, so the domain is saying I can have every number. And remember that this parentheses here says I can't include 2, right? So it's like I'm coming all the way up to the number 2, but I don't get there. And I'm going to union that with not quite 2, everything above that, right? That's interval notation in that particular formation. Okay. So that's the domain of that particular problem. What about this next problem over here? I have h of x is equal to x minus 3 over x to the 4th plus 1. Domains are about what possible values can go into the function, right? It's input values. X is, in this particular case, that's our independent variable. What values am I allowed to input into the function that then give me an output? And we know from over here, I'm not allowed to put a 2 in because it causes the function to be undefined, right? It gives me a 0 in the denominator. So looking at this one, if we hone in on that denominator again, x to the 4th plus 1, if I wanted to set this up algebraically, x to the 4th plus 1 is equal to 0, x to the 4th is equal to negative 1. Can I take the 4th root of a negative value and get a real number back? That's what we're thinking, real numbers here. No, right? No, I can't take the 4th root of negative 1 and get a real value. So when you come across this, what that says is, okay, there doesn't seem to be a number that's going to cause the denominator to be equal to 0, right? That's what it's implying. And if you second guess yourself, go back to the problem itself. Let's just pick a negative number, right? Let's just pick negative 1, right? That's a negative number. A negative number raised to the 4th power is positive or negative? Positive. Plus 1 would be positive, right? Okay, or positive. 0 plus 1 is going to be
1.
Positive and 1. 1 or 10, whatever number we choose, raised to the positive number raised to the 4th power is going to be something big and positive, right? plus 1 is going to be 1 more. Not one time in there am I at 0, am I?
Mm-mm.
So in other words, the domain of this particular function says all real numbers. If you were writing that in set notation, it would be surrounded by sets, squiggly brackets, right? X such that X is all real numbers. That's the set of all real numbers, in other words, right? If I was looking at interval notation, how would I represent the interval notation for all real numbers? That's right, negative to positive infinity.
I have a question. So like, if we took the fourth root of X and did it on the other side, wouldn't it just be like X still equal to +1?
Is there a number that I multiply it by itself 4 times that's going to give me a negative value?
No.
Then no, you can't take the 4th root of it and get a real number. Okay? -1, I could take the cube root of -1, right? And I would get -1, wouldn't I? -1 times -1 times -1 is -1, isn't it? Yeah. Don't overthink that. Just go with, can I take the 4th root? Could I take the square root, of a negative number and get a real value? No, that's when we get imaginary numbers, right?
So
That's when we get complex numbers.
So basically what you're saying is like, if we're in that type of situation, we would just like, basically whatever root we use, that spit back out that number that it equals to?
Yes,
Okay.
yes, you're gonna take the root, the 4th root of both sides, because that undoes the exponent. So let's look at this last one here. G of X is equal to -2, times X squared minus 4 over 3 times X squared plus 4X plus 4. Okay? I'm only interested in where the denominator is 0. That's what I'm asking in this question. What is the domain? What are the possible values that I can find for this function, or what are allowed as far as X is concerned? So I'm going to take the denominator here, and I'm going to set it equal to 0. 3 times X squared plus 4X plus 4 is equal to 0. Well, 3 divides off, doesn't it? So if I divide both sides by 3, I'm just left with X squared plus 4X plus 4. Now, what does that factor into? First term is a perfect, I got 3 terms here. The first is a perfect square. The last is a perfect square. So this is a perfect square trinomial, as a matter of fact, right? So this factors into X plus 2 quantity squared, or X plus 2 times X plus 2. Solving this, right? Solving this, I can say that X is now equal to -2. That is solving the denominator. I found X is equal to -2. So -2 becomes the bad guy here. He's not allowed in the denominator. And so the domain of the function is every number out there but -2. And so we can write it as X such that X cannot be equal to -2. That's the number not allowed. That's the domain. Any number out there is okay, except for -2, because it's going to cause the denominator to be 0. Domains are about what numbers are allowed for input for me to be able to get an output on the function. And if the input causes problems like a 0 in the denominator, then we can't use that number. That's what the domains are about. All right? Questions?
I'm still confused with the 4th root of -1. So why is it that a cube root would work, but a 4th root would not? I'm still not understanding.
I'm just saying you can take the cube root of a -1 and come out with an answer, right? A real answer.
I don't understand why you get a real answer.
Because can I take -1 times -1 times -1, and I would end up with what? -1. So I could take the cubed root of it, right? Because it multiplies by itself 3 times. So the cubed root would be what number, when multiplied by itself 3 times, gives me -1.
Okay.
I can't do that with an even powered function, because anytime I multiply numbers together in even increments, I only get positive values, right? So this doesn't work. The only way I would get this is if I had an imaginary I to be able to tack onto it.
Okay.
Okay? Domains. Now let's change gears and let's talk about just vertical asymptotes. You told me vertical asymptotes are those imaginary lines that our function is going to get very, very close to, but it will never cross. Okay? In theory, it's never going to cross it. All right? So we're going to look at vertical asymptotes. Now, when we think about vertical asymptotes, all right, we're going to do 2 things here. The vertical asymptote is that point where the denominator ends up being 0. So it's very closely related to a domain, but there's a little bit of a difference. When we think about vertical asymptotes, to find those, we're first going to reduce our function. And then we figure out where is the denominator equal to 0. But we first have to reduce the function. We reduce fractions by canceling common factors, right? That's how we reduce fractions, is by canceling common factors. So we're going to reduce our rational fraction. We're going to reduce it first, and then we're going to take the leftover and solve it for 0. So I have a couple examples here. The first one says x plus 3 over x minus 1. That's our first function. And I want to think, is there anything common I can reduce it with? Can I reduce, in other words, f of x? No. And why not? What is the only thing that I can cancel when I'm reducing?
X.
No.
I mean, like that you can't cancel.
I can only cancel factors, right? I cannot cancel when I'm summing or subtracting, right? So I've said this before, but I have many students who will come in here, and a lot of you actually did this on your trig when you were solving equations. You canceled incorrectly. You can't cancel these x's. All right, I have many people who want to cancel these x's, but I cannot cancel them because they are not factors. Order of operations say that I have to do, remember order of operations, right? Please excuse my dear Aunt Sally, right? Please implied parentheses or grouping symbols, right? The fraction bar is in fact a grouping symbol. And it says I've got to add 3 in the numerator. I've got to subtract 1 in the denominator. And then I get to divide, right? That's what order of operations tell me. So if I come in here and cancel those x's off, I just, violated the order of operations, okay? All right, so there's nothing to cancel here. Now I can move on and I can set the denominator equal to 0. X minus 1 is equal to 0, so I find that the equation for the vertical asymptote is x equals 1. All vertical functions have x equals as their equation, right? So I just found out that the vertical asymptote for this function is at x equals 1. Don't confuse that with the domain, okay? Don't confuse that with the domain. All I know is that right now I have a vertical asymptote at x is equal to 1. Yes, ma'am?
So I know that they're two separate things, but would this also be the domain, like if we were to?
Yes, and I'll show you what that's gonna look like in just a second. So next we have this problem right here. R of x says x over x squared minus 4. There's nothing to cancel there, so we take the denominator, set it equal to 0 and solve. X squared is equal to 4, so x is equal to a plus or minus 2 when I take the square root of both sides. So now I have two vertical asymptotes. One is at x is equal to positive 2, and one is at x is equal to negative 2. Two vertical asymptotes. The domain is 2 and negative 2 are not allowed, but everything else is allowed, right? Letter C says x squared over x squared plus 1. Can I cancel anything? Not yet, right? So when I take that denominator and set it equal to 0, I have x squared plus 1 equals 0, or x squared is equal to negative 1. Can I take the square root of negative 1 and get a real number? Then that means there's no asymptote. There's no vertical asymptote. There doesn't have to be. No vertical asymptote. We don't have to have vertical asymptotes. We just have had them up until now.
So if it doesn't spit out a real number, it's number one.
Yep. Okay, now finally we have this last one. We have a binomial in the top. We have a trinomial in the denominator. Can I cancel anything? I don't know, not until I factor. Okay, this is the first one we've had where I can factor. So I'm going to factor the numerator into x plus 3, x minus 3. And I'm going to factor the denominator into x minus 3 times x plus 7. Now, a little hint when you've done these for a gazillion years like I have is if my numerator factored, I'm going to probably think one of these factors, I'm going to cross my fingers that one of these factors might also show up in the denominator. So it kind of helps me factor it faster. Okay, but what do I have? I have a common factor of x minus 3, both in the numerator and in the denominator, right? Okay,
Cancel them, right?
so I can cancel that common factor. So now the only factor I have in the denominator is x plus 7. That's what we set equal to 0. And we find that we have an asymptote, a vertical asymptote, where x is equal to negative 7. Anybody know what happened here? We just count this guy out, move on. This becomes a hole. All right, this is a hole. When you have factors that cancel, and we'll graph this in a few minutes, but this doesn't just disappear. It's actually a hole, all right? The hole is when your factors cancel. The vertical asymptote is the factor equal to the leftover factor equal to 0. So this is different. What would the domain be of this function? X can't be equal to what?
-7.
Negative 7 and positive 3. That's the domain. The domain says you can't have a negative 7 in the denominator and you can't have a 3 in the denominator. That's the domain. Those values are cut out. But at negative 7, we have a vertical asymptote. And at positive 3, we have a hole. Okay? That's how those play together. So those are the vertical asymptotes. Okay? It's where the denominator, once it's factored, is equal to 0. Now we're going to talk about these types of asymptotes. These are horizontal or slant. Sometimes you see them called, let me think, what else was slant? Oblique, thank you. Slant or oblique is also another term for oblique and slant are synonymous. I would suggest you write this down. Funny enough, when we get to calculus, we're actually going to take the limits of our rational functions and see where this comes from. But for now, it's good enough if you write this down. Okay? What this says is we're going to evaluate the degree of the numerator, which we're calling little n, and we're going to evaluate it to the degree of the denominator m. So I am defining the degree of the numerator as n and the degree of the denominator as m, okay? And I'll explain this in just a second when you're done writing it down. Okay, write faster, take a picture. Go back in, fill it in a little later, right? Gotta move on. The notes are posted. It's also in the book. It's in the video now too. All right. So if I'm talking about the degrees of the numerator versus denominator, when the degree, and do we all know what I'm talking about by the degree? If we have a polynomial in the numerator, we can talk about the degree of the polynomial being 1, 2, 3, blah, 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 right? A third degree polynomial and so forth. So when the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote at 0. That's it. No changing of that. When the degree of the numerator is less than the degree of the denominator, there is a horizontal asymptote at y is equal to 0. If the numerator and the denominator degrees are equal, then we have a horizontal asymptote that's occurring at their coefficients, at their leading coefficients. I'll show you what that means in a minute, right? That leading coefficient. So we would have y equals to a horizontal line at those coefficients. Now, if the degree of the numerator is greater than the denominator by only a power of 1, if it's 1 more than the denominator, we have that slant or oblique asymptote, okay? And if it's 2 or more, we don't have any horizontal or slants. Okay, we just don't have a horizontal or a slant asymptote in that particular case. So let's look and see how we evaluate. I've got 4 examples here that are going to show us what this all looks like. So in this first one that we see here, I want to just know if there is a horizontal or a slant. You're never going to have both. You don't have both horizontal and slants. One or the other, or none. So the degree of the numerator, what's the degree of the numerator here?
1.
All right, what's the degree of the denominator? So 1 is less than 2. So the numerator is less than the denominator. That implies we have a horizontal asymptote when y is equal to 0. The hardest part about this is just remembering these kind of rules. That's all. Okay. Let's look at B. B says 3x to the 4th minus x squared over x cubed minus x squared plus 1. What is the degree of the numerator?
4.
What's the degree of the denominator? So we are 1 more in the numerator than we are in the denominator,
So
right?
would it be a slant asymptote?
We have a slant asymptote, and we find slant asymptotes by doing long division. This is why we had to practice long division the other day, okay? So this is a slant. This is a slant, and we use long division. Now remember, long division says I'm going to take the denominator and divide it into the numerator. So we have x cubed minus x squared plus 1 dividing into 3x to the 4th minus, we'll leave it as 0x cubed minus x squared. Yeah? All right. How do we do the long division? The long division is done just like we did it with actual numbers. I'm interested in figuring out what would I multiply x cubed by to turn it into 3x to the 4th. 3x, right? 3x. Now, the most common mistake here, I always like to surround my divisor or the guy that's on the outside here. I like to surround it with parentheses as a visual reminder that I now have to distribute my 3x into all 3 of those terms. So 3x times x cubed would be 3x to the 4th. 3x times negative x squared would be negative 3x cubed. And 3x times 1 is actually just 3x, right? So I need to move it over and line it up underneath an imaginary value over there. It's like place value, isn't it? Now, what's the next step that you have to do? It's a 2-step process when you do long division. What do I need to do here? I have to change the sign of every term in here. Don't just subtract the first one. That's the second mistake students make. So I'm subtracting every term. So I have to change the sign of every term. Okay? So my first term there is going to disappear. That leaves me with 3x cubed minus x squared minus 3x. And you start over. What would I multiply x cubed by to get 3x cubed?
3.
Right, plus 3. So 3 times 3x cubed would be 3x cubed minus 3x squared plus 3, change my signs, and it actually doesn't matter because at this point, I now have, and I'm just going to stop there. When I subtract, or when I add, I guess, 3x squared with a negative x squared, I have 2x squared, correct? Okay, well, that is all of a sudden less than what I'm dividing into it, so I've now come into the remainder portion of this, right? Because this is actually less than this right here. It's less than what I'm dividing into it. That means we have a remainder. And I can stop here because when we do long division on this, notice what I have here. What did I find on top of my house?
3x plus 3.
And what type of a function is this?
Linear.
This is a linear function, meaning it's a line, correct? Okay, and my slant asymptote would be a line. And so that right there, 3x plus 3 is the equation of my slanted asymptote.
So the remainder doesn't matter.
Nope, because all I'm doing is dividing into it to try to find out what the slant asymptote is, and it comes from just this single division.
So
2x squared is less than x cubed minus x squared.
So if you did division, right, if I did 3 into 17, right? And if I found out if I had, let's see, that's when you kind of end up with decimal values, right? Do some long division to prove it to yourself, but that is what happens. Kind of a rushed example doesn't help you, but yes, this is less than what we started with, meaning that it's now a remainder. So 3x plus 3 is the slant asymptote. So far we've seen a horizontal asymptote at 0. We've seen a horizontal asymptote at the, we've seen a slant asymptote. All right, now let's look at these two down here. This one on the left, 8x squared minus x plus 2 over 4x squared minus 1. What is the degree of the numerator? Alright, and what's the degree of the denominator? Okay, so now we have that. The degrees are equal, so the equation for the horizontal asymptote comes from the numerator's leading coefficient of 8 divided by the denominator's leading coefficient of 4. 8 over 4 is really just 2. So I have a horizontal asymptote where y is equal to 2. That's what that one looks like. All right, the last one is 2x to the 5th minus x cubed plus 2, x cubed minus 1. So the degree of the numerator is 5. The degree of the denominator is 2. 3 is 3. 5 is greater than 3, but it's 2 times, it's 2 more than 3, isn't it? Correct? So if the whole idea of division, long division, is that with that slant asymptote, I come out with a linear equation, right? I have my asymptotes are lines. They're vertical lines, they're horizontal lines, they're slanted lines, right? Just envision if I were to divide x cubed into x to the 5th, or even if I had x to the 5th over x cubed, that reduces down to be a x squared function, doesn't it? X to the 5th over x cubed reduces to be x squared, correct?
Yes, ma'am.
Well, that's a parabola, isn't it? That's a curve. So anything larger than a difference of 1 between the numerator and denominator no longer produces a line, it produces other functions. And that's not what we're interested in finding. Okay, so that's how come that one doesn't work for us. So there are no horizontal or oblique, slanted, asymptotes. Okay? All right. Now that you kind of have the components, the domain, vertical asymptotes, horizontal slant asymptotes, let's see if we can practice graphing a few of these. So the first one that we're going to look at is the function 4x over x squared minus 1. And these are the steps that we're going to follow to be able to produce the function or produce the graph. Okay? We want to factor it and reduce it. We want to find those x and y intercepts. We want to find the asymptotes. Put those on the graph. Test some points because we're practicing this for when we do move it into calculus and do curve sketching, and then finish off the sketch using our graphing calculator. Okay, so for the first thing here, I know I say factor and reduce, but let's take just a moment and determine, just because it's a good time, what would the domain of this function be? How do I find the domain of this function?
Take the denominator.
All right, so the domain is going to be x squared minus 1 is equal to 0, or x is equal to plus or minus 1, right? That's the domain. That x cannot be equal to plus or minus 1. Those are the numbers not allowed. So remember that when I'm finding domain, I want to look at the values that cause the denominator to be 0 before I ever factor it. So it's kind of a good thing to maybe answer that question if you're being asked that question. All right, now, if we're looking at the function, can I reduce that function? 4x over x squared minus 1, can I reduce it? No, I can't reduce it. So that kind of is a null point here. The next thing I want to do is I want to find out what the x and the y intercepts are of this particular function. So for the x-intercept, right? I am going to set the function equal to 0 and solve. So I would have 4x over x squared minus 1 is equal to 0. Then I'm going to multiply both sides by the denominator, and I find out that 4x is just equal to 0. Then I find out x is equal to 0. So I have an x-intercept at 0, 0. Now let's find the y-intercept. That's where we let x be equal to 0 and we solve.
How did you get y equals 0?
Because I'm looking for the x-intercept.
Oh,
So if in this one, when I look for the y-intercept, y is going to be equal to 4 times 0 over 0 squared minus 1, which is still just 0, right? 0 in the denominator divided by anything, as long as it's not 0, is still just 0, right? So I have, basically I have the x and the y-intercept are occurring at the origin, are they not? Okay, 4 times 0, Javi, is 0. Divided by -1, what's 0 divided by -1?
Two.
There you go.
What I wondered is like, so what did you do with the x squared minus 1 on the x-intercept? Did we do anything with that?
I multiplied both sides by x squared minus 1, right? I multiplied both sides by the denominator. All right, so we have our intercept. Now let's look at asymptotes. So at this point, when I want to find asymptotes, I'm looking for vertical asymptotes and I'm looking for horizontal/oblique asymptotes. All right, so those two things, they're handled separately. So for my vertical asymptotes, I set my denominator equal to 0 and solve. The denominator was x squared minus 1. And we know that when we move 1 over, x is equal to plus or minus 1. So I have two vertical asymptotes at x equals 1 and x equals -1. Now I'm going to talk about my horizontal/oblique or slant asymptotes. Remember, the function was 4x over x squared minus 1. Horizontal/oblique ones or slant ones means we compare the degrees of the numerator to the denominator. What's the degree of the numerator?
1,
What's the degree of the denominator?
2.
So 1 is less than 2. We have a horizontal asymptote at y is equal to 0. All right? Okay,
Oh.
so far so good?
Yes.
We're just walking through the steps here. So we have, let me get myself some room over here. So what I have here is I have at the origin, I have the x and the y-intercept, right? I have a vertical asymptote occurring at
1 and -1, right?
+1, -1. So I'm going to sketch those in. And I'm going to label x is equal to -1, x is equal to +1 on my graph. I have a horizontal asymptote at y is equal to 0. So remember, if that is the case, we extend the line out as a dotted line to indicate that's where the asymptote is at. And we would say y is equal to 0. So all I've done is put onto my graph the asymptotes as well as the intercepts. Now let's test some points. So similar to the test that we did for polynomials, I'm going to come over here And I'm gonna put down here like a zoomed in version of my x-axis. So I have -1 is an asymptote, 0 is an x-intercept, and +1 is an asymptote. And I want to know what's happening to the function right around these key points. All right, what's happening?
It's not touching those points.
Nope, it's not, but I want to know, is the function below the x-axis? Is the function negative? Is the function positive? That helps me decide that helps me graph it, even though I can throw it in the calculator. So let's pick a value to the left of -1. How about -2? That would be to the left of -1. Let's pick a value in between -1 and 0. How about -1/2? And +1/2 to the right and +2 at the end, okay? And you're going to evaluate the original function here. You're gonna put that in your calculator. You're gonna make sure if you need to surround the numerator with parentheses and the denominator with parentheses. Then I want you to go to your table function and tell me what the values are. I want to know really whether or not the function is positive or negative in those test places. So everybody make sure you get this in your calculator right now. You should have the function written down on your paper.
Oh, it's here. So Q positive.
Okay, do we have some values using the table function as well? The test points? Yeah, test these values, -2, -1/2, 1/2, and +2, because those are the values to the left and to the right of our critical numbers that are asymptotes as well as intercepts, x-intercepts. Okay, do we have some values?
Yes, ma'am, they're all the same.
No, they shouldn't be the same.
2.667,
Okay, so to the left, do you have a positive or a negative value?
negative.
Negative.
Okay. How about here in between -1 and 0?
Positive,
Moving to the right, what do we have next?
Negative.
negative,
And what do we have last?
positive.
That's telling me that for the function to the left of the x, to the left of -1, the function itself is going to be negative. The function itself is going to be below the x-axis. In between -1 and 0, my function is positive, so it's going to be above the x-axis. Between 0 and 1, it's negative, so it's below the x-axis. And then on the right over here, the function itself is positive. And if you go to your graph, everybody go to your graph part of your graph, that's what it should look like. You should have something that looks like that.
That's what I
Okay.
got.
I'm not too technically concerned with any of these other critical points. What we want to become familiar with is a zoomed in picture, like I said, of your x-axis. I'm going to test values to the left and to the right of what we're going to start calling critical points, critical values, which are asymptotes and intercepts. And I want to know, how does this function behave to the left and to the right of that? Okay, so these are the steps that we're going to follow as we move forward. Questions before we go any further? Everybody got that? Okay. Let's look at this one then. x squared plus 3x minus 10, x squared plus 8x plus 15. I really don't know what the domain of this function is without trying to factor the denominator anyway, so it's probably a good idea for us to factor it as that's the first step. So for this function, the numerator factors into x plus 5, x minus 2. And the denominator factors into x plus 5, x plus 3.
So could we cancel out the x plus 5?
That's what we're gonna do to reduce it. Before I do that, I'm going to just make a note over here. What would the domain of this function be? X such that x cannot be equal to -3 and -5. Okay? So the domain comes out of the function before I ever reduce it. Now let's reduce it. And we have the function f of x is equal to x minus 2 over x plus 3, which is what we're going to use as we move on. That's the function we're going to be using as we move on. Okay? So we kind of reduced it down and we're going to look at it from there. Now, before we go any further, we are going to handle this so we don't forget it. Because I canceled these factors, what did we say happened there?
There's a hole.
We have a hole. So I'm going to come over here and I'm going to address the hole. I want to know what's the ordered pair that's representing that hole. And I can find it by plugging in the value that causes the denominator to be 0, right? So that -5, it's at -5 that we, when x is equal to -5, we have an issue, right? That's where we have the hole at. So I'm going to evaluate the function at -5, and I can just do it using the simplified version here. So I would say -5 minus 2 over -5 plus 3. Which would be what, -7 over -2? Or positive, we'll call it 3.5 because that's easier to graph. 7/2 would be 3.5. So I have a hole now. Remember, a hole is a location which is going to be represented by both an x and a y coordinate. So I have a hole at -5 for x and positive 3.5 for y. Circle it so I don't forget that I had a hole there. So we had a whole lot going on here at the beginning just by finding the domain. When we cancel the common factors, we might want to go ahead and take care of that hole before we get too much further because it's easy to forget it. Okay. And moving forward, like I said, I'm going to simply use this reduced function to now find the intercepts, right? So to find the x and the y intercepts, right? That x-intercept is where we plug y in, or we plug 0 in for y and we solve. So set the function equal to 0, in other words, x minus 2, x plus 3 equals 0. Multiply both sides by x plus 3, which is the denominator. In essence, every single time is getting rid of the denominator, isn't it? Okay, so I have an x-intercept occurring at 2, 0. To find the y-intercept, we let x be equal to 0 and we solve. So 0 minus 2 over 0 plus 3 would be -2/3. So I have a y-intercept occurring at 0, -2/3. Everybody good with the y-intercepts and the x-intercepts? Okay, now let's find the asymptotes. So the vertical asymptote occurs where the denominator is equal to 0. The denominator of x plus 3 equals 0. So I have a vertical asymptote when x is equal to -3. Now, if I talk about the horizontal and oblique asymptotes, what's the degree of the numerator?
1,
Okay, and what is the degree of the denominator?
1.
So when the degrees are equal, we have a horizontal asymptote occurring at the coefficient of the numerator over the coefficient of the denominator. The coefficient in the numerator is 1, denominator is 1, so I have a horizontal asymptote at y is equal to 1. Okay?
So what you mean by coefficient, you mean like the degrees of it?
Now, the
coefficient of
degree tells me that, now the coefficient, so this is my function over
Yes,
here,
ma'am.
right? So the coefficient is
That's
that,
what I was asking.
that coefficient is a 1 over a 1,
Oh,
and 1 over
yes,
1 is 1.
That's what I was asking.
Okay, now, once we do that, we're gonna kind of put our information on our graph. So you have a vertical asymptote at x is equal to 3. They do mean -3. I was going in that direction, but I just didn't say it right. So x is equal to -3. I have a horizontal asymptote where y is equal to +1. I have an x-intercept at 2, 0. And I have a y-intercept at 0, -2/3. Somewhere right around there. Now let's test some points. Remember, this is where we're kind of zooming in on that x-axis. And I'll just stay in this area here so we can kind of see it. I have an asymptote at x is equal to -3. I have an x-intercept at +2. Those are what we would consider critical numbers. And I'm going to test values to the left, in the middle, and to the right. Okay, so all I want you to do is test those values and tell me where I'm positive and where I'm negative. You've got to graph it anyway, so plug it into your calculators. The original function, not the reduced one, plug the original function into your calculators and tell me whether we're positive or we're negative.
Which side? Or what, the -3? Probably.
Okay, so we have a positive value to the left of -3. Right, what do we have in the middle? Did you say something? Negative in the middle? What about to the right of +2? What about to the right of 2? Okay, everybody clear where those numbers are coming from? We're picking numbers, right? So Jimmy, what number did you pick here? To get that positive, it's in your calculator, what number did you pick?
Actually, sorry, -4.
All right, so if you evaluate the function at -4, you get back negative value or positive values.
But I'm getting back a negative value.
You should get back positive values. Okay, if we evaluate the function here at negative,
Oh.
in between negative, so in other words, if I evaluated a number between -3 and 2, not those two numbers. Pick a number in between, you should get a negative value, right? Does everybody get that? Yes? All right, now, the thing that I didn't put on here that we need to put on here is I put a hole here. I put an open circle here representing the whole of the function that we calculated at the above, right? Remember, we found that at the ordered pair, -5, 3.5, we had a hole. So I know that to the left of the asymptote, my function is positive. So it looks like this. I can see that from the graph. It's above the x-axis. Now I have negative values up to +2, and then the function turns positive. It looks something like that. Approaching the horizontal asymptote here. It's not a very pretty curve, but it's kind of the point. You get the point.
So that first curve just go through the hole.
No, it doesn't go through the hole. It just, it goes up to the hole and it skips over it and then it picks up on the other side of the hole.
Oh, okay.
Okay, they don't show up very easily did it show up on your calculator, Jim? The newer ones, sometimes it does and sometimes it doesn't, okay?
Yes, actually, it's a very, very.
Yep. So the newer ones does show the hole, the older ones don't always show the hole, okay? It's there. All right, yes, ma'am?
Just to clarify, to find out it's positive, you can use any number or just the ones in between -3?
I can use any number to the left of -3. And here I can use any number between -3 and +2. And then any number to the right of +2, not those numbers themselves, okay? All right, last one that I'm gonna do for you, and then you've got two you're gonna work on your own. X squared minus x plus 1. X squared minus x plus 1 over x minus 1. Okay. Will this factor? No, there's no factors of 1 that are going to subtract or add, excuse me, there's no factors of 1 that add to give you 1. Okay, so this doesn't factor. What would the domain of this function be? Okay, let's practice just for a second. X such that x cannot be equal to 1. That's called what type of notation? Set notation, because of those set brackets. If I want to write it in interval notation, it would be -infinity to 1 parentheses union 1 comma infinity. That means I'm taking all the numbers on the interval from -infinity up to but not including 1. And all the numbers not including 1 onto infinity, I have a break in it, right? Okay. In the previous example up here, interval notation would be clunky because it would be -infinity to -3, union -3 or -infinity -5, union, -5, -3, union, -3, infinity. I hate that, right? Just say X cannot be this, move on. If you want to do it that way, it's okay. There's our domain. Let's find the x-intercepts here. That's where we set the function equal to 0 and solve. So when we set this function equal to 0 and solve, we would multiply both sides to get rid of the denominator. We already said the numerator doesn't factor, so how else do we solve a quadratic?
Quadratic formula.
Quadratic formula, that's right. We can use the quadratic formula because that works all the time. Okay? So the quadratic formula says -b plus or minus the square root of b squared minus 4 times a times c all over 2a. How many of y'all remember what the discriminant tells you? The discriminant is that,
Did it tell
Chunk
you
of
whether it's gonna be
information.
positive or negative?
that's a good guess. Tells me what type of solutions I'm gonna have. Remember, I can have 3 types of solutions, right? I can have real solutions, no solutions, or imaginary or complex solutions, right? Okay, I can touch. So 1 minus 4 is positive or negative. Look in here. 1 minus 4 is positive or negative. So this is imaginary number, right? I don't have the result of this is not going to give me anything that crosses the x-axis, is it? No, because it's imaginary. We're only graphing in the real world here. So there is no x-intercept. Because the discriminant is negative. Now, that's the y, that's the x-intercept, right? So for the y-intercept, we're gonna let x be equal to 0 and solve. So I would have 1 over -1, which would be at -1. So I have a y-intercept that's occurring at 0, -1. Now let's look at the asymptotes. So we have vertical asymptotes. What tells us the vertical asymptote? The denominator equal to 0. So x minus 1 is equal to 0. Or we have a vertical asymptote at x is equal to 1. Looking at the horizontal or slant asymptotes, what's the degree of the numerator?
2.
What's the degree of the denominator? 1. So 2 is greater than 1 by only 1 more, meaning what kind of an asymptote do we have?
Slant.
Slant. How do we find the slant asymptote?
Division.
Divide the denominator into the top. X squared minus x plus 1. So what do I multiply x by to get x squared? X. So x times x is x squared minus x. So change your signs. I really only have one left, okay? So 1 is less than this, right? 1 is less than what I have out here, so I don't have any more division to do. I'm interested only in this part right here. So I have a slant asymptote at y is equal to x. There was no more division to do. So let's see about sketching the graph for this. We have an asymptote at x is equal to 1. We have a slant asymptote at y is equal to x. What's the slope on that?
It's just a diagonal line,
Going through where?
going to the origin.
That's right. So we start at the origin. The slope on it is 1/1, right? So y is equal to x. We didn't have an x-intercept, did we? What other intercept do we have?
We have a y-intercept at -1.
Okay, so I've got 1 and, yep, I have an intercept here at 0, -1. And you can test your points. But what we have is a function that looks something like this.
How did you get the?
How did I graph this,
Yeah,
Lynn?
Yeah, the one.
So from that equation, I know that the slope is 1/1. Start at the origin, count the slope. Questions on that? Yeah,
So the only
it's
reason
just
we
long.
test the points is just to be able to determine. Pretty much.
All I want you to get out of the testing of the points is you're gonna go back and you're gonna refer to your calculator anyway. So testing of the points is old school, where it would have given us information that said, okay, well, between these asymptotes, my function is negative, so I would have the graph of it would be down here. Over here, the graph of it would be up here. It's going to become extremely important for us to have that concept down when we move into it in calculus. So I'm I'm priming the well here for what I'm doing, okay? It's not really pertinent for this, but it's gonna pay off if we can get familiar with that concept, okay? Okay. You've got 2 functions here that I want for you to graph on your paper. Using all the steps that we did before, including the testing of the critical values, all right? Right? We have 2 of them here. And as you finish, you can check your answers with me. When you get done, you can come up and get your test from me. Take it away, look at it, and we'll meet back here. Now you have a Desmos lesson on rational functions that will work on exactly what we did in class today, all right? So that Desmos lesson is what you need to consider. You don't have it's what you need to do tonight, all right? It'll be a take-home quiz tomorrow after class. Okay, if you've got questions, be sure to ask. Yeah, because I just posted it.
Really?
And this will depend on what. And that is how you do on the only way I can turn this number into a 1. I multiply it by 4. Okay. But that's less than this. Yeah. That is very.
Yeah, it makes sense how this was the, there was still
left.
there's something we could still keep doing.
So.
Uh,
It's 3, so here's 3.
Oh, because this.
Yeah, this is this. Less than what I was.
When we move on to this. When we move on.
That's when we stop.
Okay.
I'm more than happy.
When we get decimals, right? When we get decimals, we had less, we had something that's less than our.
I remember it.
Yes. Our goal. That's something. To the bottom. Because I can teach each of the factors. Oh, factoring. All right, so when I look at those, this is a final, right? All three of. So all I'm interested in are, let's focus on the last. I'm gonna ask you to get factors. So look at this. Yeah. Also, I see what I'm gonna look at that section, track. To give me positive. All I need is because I can subtract. But the factors of 6. Subtract. Now, you can't do that on the top of the numerator.
No, I mean, we can say.
Not return. You want to look for, yeah. Okay.
Like in the
Yeah.
top end line.
Can we write it like
That has to
3
be-
comes?
That's the way I would do it when there's a bunch
Horizontal. Base.
of. With that.
I thought you was factors. But then there can't really factor 3x squared times 3.
They did, you factored it correctly.
I mean, yeah, I mean, you can, but you get this.
Okay, but it doesn't do it. It doesn't help it,
Exactly.
but you still need to do it,
And so I got this far.
because that's the denominator, and where the denominator is equal to 0 is, before you cancel, is where what the domain is.
So I got the
Perfect.
domain, and then I was gonna use quadratic formulas, but I don't know what I'm saying. Which I guess I'm solving for this.
You said it's 0.
Which one are you setting to 0?
To find the x, you said
The function, the whole thing.
the whole thing is 0.
Mhm.
You didn't solve for it.
So
Yeah, how do you get something like that?
y equals 0, so that'd be the x-intercept. Oh, so we're solving for this x-intercept.
So that would cancel out.
Multiply the denominator on both sides
Just get the x.
times x plus 1, which is actually easy to now solve for.
Wait, once.
Or minus 1, because there's not a product.
Minus 1.
Equals 0. Well, that's pretty easy to solve. No.
How would you?
Use the 0 through property. And this is the whole point of us solving and setting equal to 0, so I can take each of the factors and set them equal to 0, right? So I don't want to divide. Why would, I'm going to take
Okay,
3x
so
and set
yeah,
equal
okay,
to
yeah.
0. I'm going to take x minus 1 and set equal to 0, right? 0 root property. Okay. Yeah, well, or algebra 1.
All you would do is just set x minus 1 to 0, you wouldn't worry about the 3x.
No, I would set each of the factors equal to 0.
But is that for x and y?
No, that's
You
just
can't
x
reduce
and
anything. You did factor it, and you reduce it.
And then this is for the y intercept.
So if you can't reduce it, it's basically just not worth trying to factor.
It already is factored. You can't factor it. But why do you want to factor it? Well, if I'm looking at only this denominator here, I don't know what the domain is. It was helpful to have it factored. And when I solve this function to find the x-intercept, it's helpful to have it factored because it kind of shapes off the steps. So it's not a waste of time, but there's nothing to cancel. Okay, good, move on.
Also, just don't worry about factoring, we just continue from there.
It already is factored.
That's all I'm saying.
You don't cancel anything. You don't cancel anything. Right, you don't reduce it.
Is there not a y?
So the x-intercept is 0.
When you factor.
The reason why I
These
have
are-
See, I thought you asked That makes sense. I was looking at this. And I was saying,
Once you factor it,
She was wrong, but I figured it was.
and then the numbers.
That one. The bottom one is just factored.
So then, like, when it gets to further steps, like, wire and stuff like this, we have it like this.
So,
And the later steps, these two.
So don't worry about this, because don't you to have it, this one is this, for the, what you call it? X-intercept. 301. Yeah, 73. You set y is 0, so you multiply This that would build cancel out the denominator.
The numbers
All
on the
that.
page.
It's
I
hard.
wanna know how that function itself.
So it's basically the set this equal to 0 and solve it, right?
Are you asking?
Sure, I can answer some.
So what we're doing is I'm only basically assuming it's gonna set that. And I'm gonna write down what's happening here. That's an average of -3. And right here, I have 2, right? I'm focusing in on those things and I wanna know what is the function doing to the left. So that's this right here. So we're gonna end up calling these to the side. So I'm focused, I'm hyper focused on just the x-axis and where we're crossing. Where we're gonna- And plug into your calculator. So we set our calculator up last night. So I don't- Is your set up? Yeah. So if you go to second window. We're gonna change this to the axis, arrow down here.
Sitting there.
Yep. So what it says right now is the calculator is defaulting to starting at -4 in the table and increment. I don't care about that. I want to specifically ask it for values and I'm not going to scroll through. So if you go back to the right, what function is that? Is that the one that you're asking about?
Yeah, you said it.
You're just sitting there, you just saw. Sounds-
When you're doing the horizontal, you were saying, you were taking off the degree. Right, the degree tells me how to handle it, that it's gonna be. The actual value comes from the heating coefficient. So in my example, the little guy had a heating coefficient of 8. Right? It is 8 over 4. 8 over 4 is 2. Go back. Okay, so now go to your table. So these degrees told me that it's this scenario here. Oh, and then that's where you got, yeah, A over B. So that is, okay. Or A over A. Okay, okay, now your calculator is actually waiting on you. And so let's pick a number smaller than -3. Yeah, okay, so -2. All right, now, pick a number. So this is saying that to the left, the function is positive. Here, we're saying that the function is negative up to the critical value of 2. Yeah. And now pick a number. So pick 3. So you take but, so you can't see your.
So you reduce it.
So why?
Just.
So this is your degree. This is an actual. There you go. Okay, and then when I grabbed mine's still high. Because whatever I did originally, there was
I'm just gonna
still all
do it.
those scatter plots from one of those things that I did the other day. You should have turned it off. You did already. Otherwise, Go up. It is. And then it should not be correct. Okay.
Yes.
Yeah.
So we want to know what the y-intercept is. Right? Because 3 times 0 is gonna negate your this. The 0 times that. Yeah. And you should have 2 intercepts.
Yeah. X equals one, X equals one.
So if you were to look for like, so y-intercept, we're supposed to set, multiply it by the.
Yes.
So basically, how can we solve this to get the s-intercept?
So I'm gonna set it equal to 0,
Yes, ma'am.
the whole thing.
That's what I did.
Okay. But so once you have factors that are equal to 0, then you set each of the factors equal to 0. Don't go backwards. You're undoing the hard work that you've already done.
Also, we do like 3x equal to 0 and x minus 1 equals 0, and so we would have 2 y-intercepts.
Two.
X intercepts.
Yes, you would.
That makes sense.
Yeah. Is it? Is it a vertical asymptotic?
Sorry.
Because why? Did you factor these in against common factors?
The second.
So you put in the,
So the numerator factors into what?
Oh,
Well, you already factored it out. You already factored it one place, right? It doesn't affect, y'all figured out that. You have to learn how to. You're using the quadratic formula, is that what you said?
Yeah.
Yes, you can use the quadratic formula always works, but it's not very efficient. All right, so this is the way I see it, all right? These are trinomials with a leading coefficient of 1, right? Most basic one of
That's
practice.
what I.
So if I am only honing in on the 12 in the numerator, right? Over there on the right. The 12 in the numerator, then what's the sign next to the 12? You're either gonna, the negative sign implies subtraction, and the positive sign implies addition. So I'm looking at the factors of 12 that subtract to give me positive 1. And the factors of 12 that subtract.
Yeah.
Perfect. That's it. Let's look at the denominator. The denominator, again, leading coefficient of 1, I'm only interested in the factors of 6 that subtract to give me negative 1.
So what else do we need?
Test.
Or. They, no,
Yeah.
2 and negative 3.
Yes, 2 and negative 3. So when I don't have a coefficient in the front, trial and error is only looking at the factors of the last term. And I can pretty much read it kind of going backwards. I read it based on the signs going backwards. Because the last term, the factors of the last term is all I'm using to get to the other term.
But the second one is positive, isn't it? The third one.
So on this one, in the denominator,
And the the denominator on the right one, it's positive coefficient. So it'd be 3 and -2 as a factor.
No, isn't the denominator there a -1? That it isn't x squared minus x minus 6. So I'm looking for the factors that 6 subtract, give me -1.
That's what.
Yes, it's the middle term. Now, that doesn't work on the numerator on the left. Because this is trial and error is 3 terms. Leading coefficient is a +1. That's all I'm focused on. Is that really? Is that right?
Oh, right, that's a whole.
So on this one, n equals n.
No, this tells me y equals something.
Oh, so you could have.
And that's an
Yeah, I was thinking because
So this is
n
really
equals
great.
m.
Ascending order. Perfect. The leading coefficient is 3. Leading coefficient is so the horizontal asymptote y is equal to 3. No, you had to have this to know how to do 4 cases. This is telling me which of those 4 cases I have. Now, once you determine which case you have, then you have to decide what to do in that case.
That's
In the problem that I worked in class, I had a leading coefficient of 3. Just doing 4 cases. Go back and look at that problem. 8x squared. Yeah, 8 over 4, 2 over 1 are 2.
And it's next.
Very well.
Actually, yeah, I printed it out. So, yeah, so.
You're not the only one who's doing this. You have to break this out. Rather than, right? The whole reason the reason we have this. Javier. Okay, so each of the factors equal to 0.
That's.
Just check over it, make sure I did. Are you all done?
Yes.
And you agree with the answers? Yeah? Okay.
Remember earlier.
Well, that's on you.
We're all there. Okay. It's not good. This one all should be just don't eliminate that.
This one I got stuck on. I actually.
Get it
Yeah. Yeah, but I'm. That's awesome. Yeah, we set up. Oh my God. I was
Might have been worse.
Yeah. Blown away. I'm really blown away. I don't know how I got that wrong.
Oh, wait, yeah, right.
All right.
Yeah, usually. You're bound to this. The only place to be. Yeah, but
And
these were.
try to come and see it on the house.
I don't know what.
House.
What I would do is if you can.
Right? Then did you get it? Yeah, this was not exactly right. This was not exactly right. Don't you have two extra?
Yes, I just got partial credit.
Oh,
That was included.
that.
Yeah, you have an intercept at one. You can't see that on your graphing calculator very well when you zoom in, but you know it's there because you just solved it out right, right? Yeah, you have to make sure that you get that.
Oh, I mean, but so there's.
Don't just rely entirely on your graphing calculator.
Okay.
Like,
I do what? So I can get. The way that I do this is, this is the way that I went about it. So, okay, well, I just do the total side, at least on first side, 6 times data equals -2. Subtract the total side, some data make it a third, and -19.7. So then I just needed to be. That was what I wrote. That's not right.
First, we want to turn your plot off.
Well, I still have those more. No, I haven't finished the whole thing.
All right, so as y'all are finishing up and I'm handing the test back, one of the things that I want you to take note of when you're looking at your test is I need you to look over your algebra, all right? The algebra on some of these mistakes that you're making, and we're moving into areas where I need you to know how to do the algebra. Just like today, when we're solving equations, the goal of factoring, right? The goal of solving when I factor is to set it equal to 0, factor the roots, and then put them equal to 0, right? It's the 0 root property that I keep talking about. Very, very important. We will use it a lot. So as you look over your test, you need to make sure you understand what you're missing algebraically. All right, and then come and visit with me. Come and visit with me if you have questions on those things. No. It's zero. Zero. That's gonna make 8. 0 over 12 is 0.
Oh, I think.
Oh my.
All right, you got a Desmos lesson?
There's experience. What did you make? I was really hoping to fail. I was really expecting to fail. I can always get those points.
I'm not.
I'm not even happy. If I go, I'm.
No, like I need to get some.
Chose negative.
I forget what
Was it?
it
Yeah. I thought you said it was for a
I also.
Jimmy,
Yes.
go over there to my computer if you would and touch the 2 points, the very last file, right there, it says 2.6 rational functions or whatever. No, my laptop.
She's about 2.6.
Yeah.
The bottom.
Touch it. Now scroll all the way to the bottom. Keep going. Keep going. Keep going. Keep going. Keep going. Keep going.
Yeah.
Keep going. Yep. Stop. Thank you. That's the answers.
Because I wanted to go from class.
Then on the other side of that one.
So there would be.
Yeah, because we're out there, right? So we're up here, and is this 3? So you would have even another. We don't have a hole. do we?
No.
Yeah, no. So now you have to add in here. The third, yeah. So we call those critical points because they're the things that are telling us how the function is behaving right around those. So at 3, I'm going to test the 4 in there. Which would be y here to the right of 3. Here to the left of negative
Okay,
4.
that makes sense. I had a question.
Pretty much.
Yeah, the non-real roots. So whenever.
Complex roots.
Yeah, the complex roots. Whenever you do are they? Yes.
Is that right? So I have a function that. Here, right? On function. So this could be, let's x cubed, which that's in here. If I had maybe x to the 5th, because that would also be an odd function, right? I only have 3 roots here that are crossing. So I have 2 more available roots
That aren't,
that aren't showing up.
okay, so that would mean that there would be 2.
Not necessarily.
It doesn't have to be.
Well, they're not, No, it does. You're right. They occur in pairs.
Okay, yeah, because that's what I was confused about, if it touched or if it would, like, if this were to be,
Well, so, I mean, there's all sorts of variations, and in that exploration that I had y'all do, right? You should play around with the exponents on those groups. So let's say that this is, we'll call this 1, we'll call this 2, 3, right? I could have x plus 2, x plus 1, x minus 3. That's a cubic function, right? But what if I had, I could have, I mean, there's all sorts of choices here, right? What if I had,
standard happening, whether it's. Good,
3, 4, 5, 5th, right? Still crossing at each of these roots, right? Even though the multiplicity is no longer 1, multiplicity is a repeated root. That's all that means. So you can see that you have all sorts of variations going on here. In fact, that's the one of the really nice things in Desmos is take a function like this, just make a hidden factor form, and then start playing with the roots on the function. You can copy and paste very easily from your keyboard, and then you can turn the function on and off to look at it. So, this one is, if it was like this, everywhere here would be a real root. wouldn't it? Because this is just saying that we're crossing there, it's just a repeated root 3 times. This is still process, it's still process. If instead I had degree and I found out that, I had the rest of this polynomial that was still here, then I would have, that's not the right way to say it, but I could have potentially complex roots that would show up.
Okay, so that means that there's 2 complex numbers. Could it also be like x to the 4th, or would that not work because there's 2 there's 2 complex roots right there?
What do you mean?
Well, like, is it 1 point or is it always 2 points?
Complex roots are going to always occur in pairs,
Okay.
but they're not points. You're not going to really see them.
Oh, yeah, I didn't.
Okay.
Sorry,
Just so you know that they're not really, you can't even really tell they're in your function because of the way that you graph, right? We're 2-dimensional. We're graphing in the real plane, right? Where the y's and the x's are both real numbers. If you add the imaginary point in there, then I think it goes down to a 3-dimensional object.
Oh, yeah, that's what I was confused about. I didn't know if they came in pairs or if they came in.
Complex numbers will always come in pairs
Okay.
because you have to graph the conjugate. So you'll always have the conjugate. And if you think about that, that would make sense because in essence, you're having to use the quadratic formula to find it. When you use the quadratic formula, it's negative e plus or minus the square root of this. So you have the plus and you have the minus. So they're always going to come. Does that help a little?
Yes, it does.
But like I said, we don't graph we don't add the imaginary graphing back. I think you do imaginary, you might do that in Cal 3 when you start graphing 3-dimensional objects. That's one reason they write this stuff down. Okay.
All right, thank you.
Oh.
That's right there.
Here, I can make it smaller so that you can kind of see. I don't think you wanted to touch my computer, but that's fine. There they are. There they are.